Now, this is the last set of slides that we have for this class, and I hope that you've learned how to make a forecast, at least on some dimension, up to this point. But I want to bring up the triple exponential smoothing model as a nice complement to the double exponential smoothing model. So if we go back to the double exponential smoothing model, how it works is you can see the sample data that we have right here, and it's trending up. Okay, and so if we were to make a forecast for this data set for period 7, it would be in the 10.5 range. Okay, that's all well and good if we don't have any non-linearities in the trend. So if you look at this data, however, sometimes it goes up by 1.8, sometimes it goes up by 1.7, 1.45, 1.6, 1.55. So we don't have necessarily a perfectly linear trend, and there may be some type of flattening or amplification of the trend over time, and we could even see a situation where the trend goes from being positive to being negative. And so we just want to try to forecast by keeping track of where the trend is. And we do that with the double exponential smoothing model, where we have a level which describes where the time series is now, and we have a trend which describes where the time series is going. And you can see here that for every period, we use the data point for the level. So x is the data. I use that in my level equation. So where do you think the time series is located today? Well, an excellent place to look is the current data. And then the old level and the old trend represent the forecast that you made, which has been decomposed into a level and a trend. So with single exponential smoothing, there is no trend. The trend is 0, and the old level is just the old forecast. But with double exponential smoothing, the old forecast has both the level and the trend. Okay, and so you can see in all of these equations, we have the previous level and trend in the level. So for period 1, I have 0.8 times the data for period 1, that is 1. And 1 minus 0.8 times the old level for period 0, and the old trend for period 0. Then our trend operates like a stair step. So it's a change in the level, and some part of it is the old trend. So you can see that we're going up by 1.5 each time roughly in column 2 where the data are located. And you can see all these trends are kind of hanging out in the 1.5 range. So between 1.5 to 1.7. And if we were to go ahead and make a forecast for period 7, which is not located here, we would actually have 9.1057 plus 1.558. So we would have a forecast that's in the 10.64 range. And that's completely consistent with what we've seen. And you can see it right here on this slide. So we don't want to do this by hand. We talked about doing this in Excel, and that is where we left off for this class. And so what I want to point out to you today is that, hey, there may actually be trend in the data. We are still very concerned about trends in the data with the COVID-19 pandemic. So are we flattening the curve? What does it mean to flatten the curve? Is the trend that is upward sloping in the level, in the number of cases and the number of deaths, is that trend, we're still going up, but is the slope flattening? So if we try to think of flattening the curve in the context of the double exponential smoothing model, are we going from 1.5 to 1.4 to 1.3 to 1.2? Or are we hanging out in the 1.5, 1.6, 1.7 range? One isn't flattening, the other is. And that's something that is of great importance, and we think of these things like social distancing, what we're doing now, we're taking this class online. But the underlying premise is that we're trying to create conditions where our forecasts for future trends are diminishing, and we would eventually like the trend of new cases to approach 0, kind of the R0. All right, so let's go back to put this in a business context, because even with this pandemic, people are still buying stuff. So let's think about a retailer in a mall. Now, I don't know what that's going to look like in the future, but let's just go back to what we've thought about in the past. Obviously, quarter 4 is the best quarter for their sales. So How it normally works is retailers operate in the red all year, they're losing money, and then Black Friday hits, and they sell so much stuff that it puts them in the black for the year. And this occurs every year. The day after Thanksgiving, people they're stuffed full of turkey, and they have all kinds of ideas about what they want to buy, and they go out and buy it. So that's quarter four. Now, quarter one, we have a little bit of buyer's remorse. We pay our credit card bills, and we see this into quarter two, where we're like, oh, geez, I bought a Peloton. I can't afford to buy anything else in quarter one and quarter two, so I'm going to pay off my Peloton bill. But then quarter four comes around, and I'm like, oh, geez, with kids and grandma, that's not good, so I better buy something. I don't have anything for the kids. Abraham, he wants Thomas the Train. Stella wants Peppa Pig, so we better buy those things. And this happens year after year. So this is predictable. Now, if I'm a retailer, my goal is to have my sales trend up over time, but I also have this seasonal cyclical pattern. And so we would like to measure this. Let's take a look at Apple revenue from 2011 through 2014. Now, I fit a trend line through their revenue data, as you can see. The trend line is, I think, indicative of what a double exponential smoothing forecast might look like if we just fix the trend to be the slope. As you can see, it does okay for some of the periods, but it always misses the spike. Okay? And so what we are going to do is introduce something to capture these peaks and valleys a little bit better. So basically, I would like to scale my prediction up when I'm in a season where I know that predictions are likely to be higher. So quarter four, I need to inflate my forecast. Quarter one, I need to deflate my forecast. And you can think of hotels doing this with high season and low season. So if you're looking at the Hyatt on Clearwater Beach, March and April are high seasons. Okay, spring break is going on. People want to go down to visit Clearwater Beach. December is a high season. We're in the Northeast. We're cold. We've got snow on our boots. We would like to go south where it's warm to the beach. Summer is a high season. Okay, now August, September, October, not high season. January, February, not quite as high season. So when people are in school, they're not at the beach. And so I priced my hotel rooms accordingly, but overall I would like, my pricing for the room to go up over time. So I don't want to charge $199 a night for the next 10 years. I'd like to charge more, but I also have to account for the seasonality. So we're going to use three items to make a forecast. A level, where we think the time series is now. A trend, same implications as before. Could be going up, could be going down. And a seasonal multiplier. The seasonal multiplier is new. So however many seasons you think you have in your model, and you need a season for every part of the year, that's how many multipliers you're going to have. So if we have high season and low season in a year, we have 2. If we have quarters, we have 4. If we have months, we have 12. The example I have on your handout for college basketball season, I generated 5. So we have a seasonal, we have to think of it like this, we have to change our forecast for every possible state of the world. So hey, it's low season, I need to deflate my forecast. Hey, it's high season, I need to inflate my forecast. The question is how. How do we do it with the seasonal multiplier? Now, the forecast, we take the level and the trend, we add them together like we did before. Maybe we multiply by the trend if we're trying to forecast a few periods out, but then we also account for the seasonal multiplier. Okay? The level equation now includes a term for the season. So where I think the time series is located may be distorted by the season that I'm in. So actually the time series may be higher than the data point currently is because I'm in low season. I have to account for that. So where do you think the time series is going? If I just have 2 seasons, ideally I think it's kind of in the middle of those 2 seasons. But at any point in time, I'm either in high season or low season. I'm not in the middle. So the level equation tries to split the difference by dividing by the seasonal multiplier that you see here. Okay, so to summarize, we're creating weighted averages of the level, the trend, and the seasonal component. We need starting points. So we're going to work on the starting points here in a minute. We need a starting level, a starting trend, and starting seasonal multipliers. We aren't going to use regression analysis to estimate the trend anymore because of the problem that we see here with the Apple revenue. So here is a regression fitting right through the data, and it does not capture the peaks and valleys anymore. So what we ideally need to do to get the trend is measure peak to peak, trough to trough, middle to middle. That's what we're going to do. So this trend initialization process, what we do is we take each data point for 2 years of data. We burn through 2 years of data to find an initial trend. So Y2 is the data point for year 2, quarter 1, and I subtract the data from year 1, quarter 1. So I measure quarter to quarter. I do the same thing for quarter 2, quarter 3, and quarter 4. So the large 2 represents the year 2, the large 1 represents year 1, and the Q's are different quarters. Now, so this trend is going to be split into a quarterly trend. So we divide by 4 to split our trend into quarters. Now, when we take these differences, we have a difference for quarter 1, a difference for quarter 2, a difference for quarter 3, and a difference for quarter 4. So it's like multiplying your trend times 4. So you also have to divide by 4 out here. So basically think of the parentheses as being an average trend for the year and the fraction outside the parentheses as chopping it up into the number of periods that you have. The season, I'm sorry, this should be, we will find the season by averaging the first year periods together and the second year periods. So I take an average of year 1 and I take an average of year 2. Then what I do is I look at the data point as a percent of the average. So if you take a look at the very last bullet point, Y1, Q1, that is the data for quarter 1 of year 1. And I look at that as a percent of the average. So maybe it's 110% of the average if quarter 1 is bigger than the average. This is bigger than 1. If it's smaller, it's less than 1. And same here, and I just take an average for all 4 quarters. I'm going to show you with an example what I mean here. The initial level is the average of year 1. Typically, the smoothing parameters are pretty small. I want to point out the smoothing parameters here, we still have alpha, we still have gamma, but we have this new smoothing parameter called delta. Delta is the smoothing parameter for the seasonal equation. And typically, they're pretty small. All right, so they're less than 0.5, and it's because of this splitting the years up into different periods. So that's why they're pretty small. And most of the time, if you wanted to do this model, you'd have some specialized package do it for you. But we don't have that for this class. We just have Excel. We're going to use Excel. Okay, so let's take a look at some data that are seasonal. And this is Amazon revenue. Now, I just grabbed it right off the internet. I have more revenue information than this, actually, but I just took this revenue because it was all I could fit on the slides. Now, there is 2012 data available, but I'm pretending that we don't have any 2012 data in this example. I have a column for the level, the trend, and the season, and for the forecast. So I'm pretending I don't have this data. It's actually available. I do have the 2013 data and the 2014 data. Now, you can see that quarter 1 and quarter 2 are smaller than quarter 3 and quarter 4. So I want smaller forecasts for quarters 1 and 2, a little bit larger for quarter 3, and then quarter 4 is Christmas. Everybody gets on Prime. Oh, I got to buy this. I got to buy that. Will they wrap it for me? No, Amazon won't do that. Or maybe they will. Let's find out. And I want to inflate that forecast. Okay. So the data split into quarters. And you can see I just kind of show you the quarters. This measured at the very last date of the period here. You can see. So if you would download this data from the internet, normally what would happen is you would get column 1 and column 4. I inserted columns 2 and 3 here to show us how to apply the triple exponential smoothing model. Okay, so let's get started. We need an initial level and trend. The first trend is for the period before we observe any data. So I'm going to try to put that in the last quarter of 2012. Last quarter of 2012. Now let's go back to the description. I'm taking period differences here and dividing by 4 and then dividing by 4 again. So let's take a look. The period difference, I'm going to take the difference of quarter 4, the 29,328 minus the 25,586. You can see that here. I do the same thing for quarter 3. I take the 2579 minus the 17092. Now this revenue is in millions. It's actually billions of dollars. So Amazon rolled in around $26 billion of revenue in 2013. Okay, these are the quarter 3 data. These are the quarter 2 data points. And you can see I have the subscripts here to describe the year 2014 minus 2013. New minus old. And same deal here. So I plug the data into this next part here. And you could, I'm sorry I left out this left parentheses here. That's my fault, everyone. Then I evaluate the top of the fraction, the numerators here. I divide through, and I got an initial trend of 908.5. Now, what does this mean? It means that Amazon's revenue is trending up $908 million every quarter. $908 million of revenue every quarter trend. That's our trend up. It is not the level, it's the trend. Now, the first level is the average of 2013. So I just add up the 2013 data that you see here and divide by 4, and that's the first level. I'm going to stick that right into the level column for quarter 4 of 2012. So I put the level and trend before I ever observe any data. And you note that this is consistent with what we did with the double exponential smoothing model, where you can see that I don't have any data for period 0, but I have a level and a trend. Okay. All right, let's go back to the seasonal multipliers. Initial multipliers, we need 4 multipliers because we have 4 seasons. Each multiplier can and should be thought of as a percent of the level. Note that I found the average for 2013 already. We just did that right here. But I need the average for 2014. So I averaged these 4 data points together. The 19,741, the 19,340, the 25,79, and the 29,328. And you get 22,247. So they're right here. Okay? Now, I take the data for 2013 divided by my estimate for the level, the average. So 16,070 is the data for quarter 1. The average is higher, 18,613. The average is for all of year 1, and year 1 includes quarter 4, which is big. So this is a year 1 data point. Quarter 1 is a little bit smaller than the year 1 average. And the same deal for 2014 quarter 1. It's a little smaller than the 2014 average. So my seasonal multiplier for quarter 1, I calculate these fractions, data divided by average, data divided by average. Then I get a fraction here and here. And the end seasonal multiplier is 0.8754. Now, what does that mean? It means that quarter 1 is 87.54% of the time series level. That's my estimate. Now, this may change over time. You may think the quarters converge to each other in certain circumstances. I then repeat the same process for quarter 2. Quarter 2, if you look at the data, is even smaller, okay, than quarter 1. So I should have a smaller seasonal multiplier. So I'm taking 15,704 dividing by the year 2013 average. That's 18,613. And I do the same thing for year 2. The data is 19,340. The average is 22,247. So the averages don't change. The only thing that's changing is the data. And I have a multiplier of 0.8565. Now, I interpret that as quarter 2 is 85.65% of the level. Quarter 3 is bigger than quarters 1 and 2, so it makes sense that the multiplier is bigger. Q4 is monstrous. So you can see the Q4, that's when everybody's on prime, spending away. 25,586, 29,328, Q4. And they're much larger than the averages. In fact, Q4 is driving the truck with the averages. So Q4 is 134.64% of the level. And what this means for us, if we go back to the triple exponential smoothing equation, is that, hey, we're going to deflate the forecast for periods 1, 2, and 3 and inflate it for period 4. And how do I tell in real life if I'm doing the seasonal multipliers correctly? Yeah, average should be pretty close to 1. Okay. So how do I put this into my table? The level is the average of year 1. The trend we found. It's those differences. The seasonal multipliers are located here. 1, 2, 3, 4. All of this is put into my spreadsheet or wherever I'm making forecasts prior to the data. So 2012 data doesn't exist. Now I know it's online. It doesn't exist for the purposes of this example. I put in these initial values to start with. Now let's make a forecast. How do I make a forecast for Q1 of 2013? I take the level. I add the trend. That is what I did for the double exponential smoothing. So the double exponential smoothing pretends there are no multipliers, but I deflate the forecast by the season 1 multiplier. So I'm making a forecast for season 1, and I deflate by the season 1 multiplier. And you can see that I still overshot. Part of this is just because the level is so large, and that will work itself out over time. You can work it out a little quicker if you inflate the multipliers for the smoothing parameters for the level equation. You can get this to be a little bit closer. But the forecast is going to overshoot a little bit and undershoot for that matter because of the imprecise way that we calculated the first level, and that's just kind of a part of it. Now, what we want to do is then use the level, the trend, and the season equations to go forward like we did with the double exponential smoothing model. So let's try it out. So I want something to put here, and here, and here. The level equation, this is for Q1 of 2013. I have alpha times the data for Q1 of 2013 divided by the seasonal multiplier, and there should be a hat there, over from 2012. So I look at inflating. I inflate my impression of where the level is because I know that Q1 is kind of a low season. Old level, old trend. So the level equation is exactly the same as the level equation. You can take a look at this level equation. Exactly the same as the level equation that we had for the double exponential smoothing model. Except we have a seasonal multiplier. So the seasons do impact our impression of where the time series is. Now, 16070, that's the data. 0.8754, that's the season. Old level, old trend, and you evaluate. Now that 19055.83 is going to go right underneath. Let's look at the trend next. Change in level. Same as with the double exponential smoothing model, no change. The seasonal multiplier is incorporated through the new level. 19055.83 minus 18613. So old level, new one we just found. Old trend. And that should be a 908.5. That's my fault, everyone. I'll fix that for the slides that I post online. In fact, I could fix it now, actually. Just fix it real quick. To make the slides, I use this program called Tech. That'll make the slides for you. All right, so let me actually reopen. I'll reopen the slides that are fixed. That way we can see the new slides. There we are, 908.5. Sorry about the little detour there. 908.5 is the trend, okay? And the old trend is located right here. Now, we have this. This is the new part. This is the new part right here, the seasonal multiplier. What this does is it updates our season 1 multiplier, but we're not actually going to use this again until 2014. So I'm going to put a new multiplier here, then I'm not going to use it, not going to use it, not going to use it, then I'll use it again. All right. Data divided by the level. So the data was 16070, and it's a percent of the level. Completely consistent with what we did here, data as a percent of the level. We just updated where we think the level is. Instead of it being the average, now we have an equation with an L in it. And the old seasonal multiplier here. And you can see I put the data in here. Now, how do I make a forecast for period 2? Level plus trend, season 2 multiplier. And you can see on the slides that I color-coded the multipliers that you're supposed to use for each season. Now, let's try to use it in Excel. So I have Excel open. I did put the Amazon data into Excel. You can see it here. Let me zoom in on it a little bit here. And I want to replicate what we did on the slides in Excel. So here's how we find. So what we're going to need is information to go for the first level. Let me just highlight that cell here. We'll make it nice and festive green. This is the initial level. I put a little note here that says initial level. Okay. And it's the average of the first year of data. Okay. So right here, equal average, first year of data. Done. 18,613. If we go to the slides, 18,613. Now the trend. I have 1/4. Let me actually put this in parentheses. 1/4 times. We're going to take the differences in each period. So I have Q4 of 2014 minus Q4 of 2013, which is D13 minus D9. And a nice thing about Excel is that it highlights the cells that you want. So I'm going to put this in parentheses and divide by 4. Okay, then I'm going to do D12 minus D8. I'm just clicking those cells, divided by 4. And then I have Q2 data. And let me just add in one more set of parentheses here. There we are. And then finally, Q1. I keep forgetting that second set of parentheses here. There I get the 908.5 that I had on this slide. Okay, we could I'm just going to leave this up for a minute so that everyone can pause at the appropriate part of the video to see how to make the trend. Now, if I had 3 periods, I'd have 1/3 and divide by 3. If I had 2 periods, I'd have 1/2 and divide by 2. If I had 12, if I had monthly data, then it's regrettable, but you do have to divide by 12. Now, one huge advantage, and one of the reasons I really think it's important for people to have a grasp of the triple exponential smoothing model is, look, if you start a business, you like to project revenues. How should I project revenues? Well, I'd like my business to be doing well. That implies a trend up, but the best description of future periods is the past and specifically monthly data. So how's this April going to look? Well, it's going to look a lot like last April. Now, if I use a naive forecast, modified naive, you might think that would help me out. It can, but if there's a trend, I also need to account for that. All right, let's look at the seasonal multipliers. Percent of a level, guys. So I have 1/2 times. You're going to take the data for quarter 1. Here's quarter 1. Divided by the average of year 1. I put the average in dollar signs strategically so that I can copy this formula down. And then I'm going to do D10. That is quarter 1. I'm going to put this in 2 sets of parentheses. You can never go wrong adding an additional set of parentheses. It's been my experience. I lock this in. Okay. So the red you can see is the average of year 2013, which is quote unquote year 1. And the green is the average of 2014, which is quote unquote year 2. And put that all into parentheses. I still had one, you can see I still had one set of parentheses too small, and I get this 0.8754. Now, here's the nice part about this. We go back to it, and you can see if I double click on it, I have this dollar signs lock it in place. The only thing that's allowed to move is D6 and D10. So if you get 1, you can copy it down and you get the rest. Okay. Now, how do I make my first forecast? I take the level. I add the trend. I multiply times the season. And I'm going to do that all the way down. How do I get the first level? Now I'm going to need something for smoothing parameters over here. So I have an alpha, a gamma, and a delta. And let's just say I use, I guess, 0.4, 0.3, and 0.2 like I used on the slides. All right, now alpha is associated with the level, so I take $I, $2 times data divided by season plus 1 minus $I, $2 times old level plus old trend. And you can see I get this 109, 19 billion, 50, 12. Now, I'll have you note that that is a little bit different than what you see on the slides. It's because on the slides I rounded down to 4 decimal places, but Excel, there's no rounding necessary. All right, gamma, that's an I3. Trend equation. Change in level. Plus 1 minus $I, $3 times the old trend, which is not listed there, which is an F5. There we are. All right, so summarize the level equation. Data divided by season. Old level, old trend. Trend equation. Change in level, old trend. Seasonal multiplier. We take delta, that's in I4, times a percent of the level. And then 1 minus I4 times old season. All right. Now, do I have a new seasonal forecast? Yes. You can see level plus trend times season 2. Now, Excel will line these all up automatically for you, so I can just copy this down here, and I have some predictions. And you can see that in actuality, we don't do that bad. We do over-predict quarter 4 for both 2018 and 2019 pretty aggressively. But you can see the multipliers are pretty consistent throughout. I would point out that one thing that you can kind of notice through this data is that the seasons are converging to each other a little bit. So we go from 1.34, and the quarter four premium for Amazon just keeps falling over time. You can see the average is still around 1 down here, but that multiplier keeps falling over time. And I think it does kind of speak, if you're thinking about Amazon, to how much people use Prime during the year. Now, over here, I have made a forecast for period 1 of 2020, which is right here. What if I wanted to make a forecast for period 1 of, or period 2 of 2020? Here's period 2, 2020. It's not 0, okay? But the problem is I have E34 and F34, and those are blank cells. So what I'd like to do is use the last known data, which is in E33, and I'm going to take this and multiply times plus 2, so I'm going to incorporate the trend. And change F34 to F33. So I juice it up a little bit more. Now, I am going to use a seasonal multiplier from season 2. Okay. Now, I'll point something out to you. You can note that the seasonal multiplier for 2019 for quarter 1 is bigger than quarter 2, but the quarter 2 forecast is bigger than quarter 1. That's because the trend outstrips the seasonality. So just kind of an interesting point. All right, so to summarize, when we do the triple exponential smoothing model, we would like to use Excel. And I have examples of how to use Excel both in this video and on your handout. So please let me know if you have questions.